Hello, everyone. Welcome to our first ever Fireside Chat of 2022. Today we'll have Rick Schutte. Rick is a Master of Architecture candidate at the University of Toronto who's excited about all things AI, sustainable design, high-speed transportation, and parametric design. Rick today will be discussing his infrastructure research related to Hyperloop, and we'll be talking about his Hyperloop team's HyperTransit Canada and U of T Hyperloop. Please welcome Rick.
Hello. Uh, Thank you for having me here. I'm going to start by just introducing myself, the University of Toronto Hyperloop team, as well as HyperTransit. Like Justin said, I'm a Master of Architecture candidate at the University of Toronto. I've been a part of the University of Toronto Hyperloop team for a couple of years now, and what we've been working on is the infrastructure side of Hyperloop development. So what goes into making it a reality, making it happen, and then how can we make projections to make it more sustainable and to be able to plan out the future of our cities with tools we have now. So today specifically I'll be talking about HyperTransit, what it is, why we need it, as well as very, very exciting system of analysis called multi-objective evolutionary Hyperloop route optimization. So first, what is HyperTransit? HyperTransit is high-performance public transit. It is transit-oriented communities, accessible, resilient infrastructure, high-speed, carbon-negative travel, minimally invasive infrastructure, socioeconomic superfuel, equitable urban planning, comfortable and safe commuting, one-click door-to-door transportation, decentralized multi-mode transportation, dynamic travel demand response, innovative civil engineering, automated maintenance, integrated vertical farming, environmental regeneration. Ultimately, HyperTransit is a growing collective of professional and student innovators. HyperTransit will mitigate the environmental impact of existing transportation and building systems. HyperTransit will mitigate future urban sprawl and habitat loss through regenerative developments. HyperTransit will promote economic growth with a resilient integrated transportation network. HyperTransit will promote social equity, inclusion, accessibility, and connectivity. HyperTransit addresses the cost and quality of contemporary Canadian life. So what is the cost of contemporary Canadian life? Here's some data showing and comparing the basic cost of living across major international cities. And this shows the average total living expenses, not even including rent, of Toronto and Montreal. And you can see that for one person per month, it costs around 1,200 Canadian dollars to live in Toronto. But for a 4-person family per year, it costs upwards of $54,000. So what is the cost of housing? In Montreal, for example, house pricing is more affordable than Toronto, but it is continually rising. For example, the household annual income required to afford the representative home is $106,000 per year, and 47 months of saving are required to make the down payment. In contrast, $205,000 is needed for a household annual income to afford the representative home, and 330 months of saving are required for the down payment. Canadian urban planning is dominated by road infrastructure, with more than 1 million kilometers of roads, with 40% of the network paved and 60% unpaved. 4 provinces, Ontario, Quebec, Saskatchewan, and Alberta, account for over 75% of the total road length. Emissions from passenger cars and light trucks account for approximately 25% of Canada's total greenhouse gas emissions. The United States spends $100 billion per year in constructing new roads and bridges, and another $100 billion each year in maintaining roads and bridges. It also recently passed a $1 trillion infrastructure bill. Beyond the cost of owning a vehicle being greater than $10,000 per year per car, roads that are inadequately maintained cost Canadian drivers an additional $3 billion per year in higher vehicle operating costs. Vehicle prices in Canada average an all-time high at more than $40,000, with the most popular loan term in Canada equaling 84 months or 7 years. This means by the time you're finished paying off your car, you might need a new one. Electric vehicles and autonomous electric vehicles are often seen as the response to traffic and to vehicle emissions. But these are not the sole answer to existing highway traffic, sustainable travel, productive travel, accessible travel, or affordable travel. But they are part of the solution. Here shows the existing and future transportation systems and the cost of their time and emissions. This top diagram here shows the driving and occupied time versus the available time of traveling from Toronto to Montreal. You can see here, driving in a vehicle, you are completely occupied during that time, and it takes over 5 hours to get there. In a train, it takes a similar amount of time, but you have more available time. You can be doing things while traveling. In a plane ride takes a shorter amount of time, but there's more time being at the station, going through security, waiting, and the available time is still shortened because of that. In contrast to future transportation systems like maglev or Hyperloop, a maglev will make the trip from Toronto to Montreal in 1 hour and 40 minutes, and a Hyperloop would make it in 40 minutes. Below here is shown the emissions, the CO2 equivalent emissions for train, vehicle, plane, Hyperloop, and maglev. And you can see the emissions of a plane is just extraordinary. Agriculture. In 2011, Canadian agriculture used 1.8 cubic meters of water. Unlike thermal power generation and other major water users that discharge most water withdrawals back into the environment, agriculture consumes most of the water withdrawn without return. Agriculture is the main source of atmospheric emissions of NH3, or gaseous ammonia, which is produced from livestock and poultry manure management and fertilizer application. When agricultural emissions of NH3 occur near major population centers, they can interact with sulfates and nitrates from industry to form secondary fine particulate matter, which can have harmful effects on both human health and the environment. In 2012, agriculture generated 56 megatons of carbon dioxide equivalent greenhouse gas emissions, 8% of Canada's total. Greenhouse gas emissions from agriculture increased 19% from 1990 to 2012. A further 14 megatons of CO2 equivalent were attributed to on-farm energy use in 2012. These increases were due to higher populations of beef, cattle, and pigs, as well as an increase in the use of synthetic nitrogen fertilizers. So, what is our plan? Our goal is to connect major cities with affordable, sustainable, and resilient transportation infrastructure and transit-oriented communities, which include vertical farming, and democratize opportunities within urban centers. We want people to be able to access the jobs and education that are within high-cost urban areas without having to live there. Here, this is a map showing major cities around Ontario and the Northeast US, and this is showing a few different things. In the background, you can see in grayscale, this is population density of Canada and US. And these big circles, this is the current annual passenger count of plane rides. So you can see in black, this is the total, in black here, this is the total annual passenger count, and in gray, this is the domestic passenger count. So in these cities that are mostly gray, these have predominantly domestic flights. So these are areas we can replace their current domestic flights with actual Hyperloop routes. And we can take those emissions out of the sky, shorten travel times, make them more affordable, and have a more resilient infrastructure. The step one of doing this is to develop a macroscopic vision for a highly connected region and optimize the network's curvature and overlap to reduce material and increase speed. You can see here, these cities from the last slide are connected with straight lines where each city is connected to at least two others. This curvature optimization aims to smooth the paths connecting these cities so that you wouldn't need to stop from one city into the next. And if you wanted to go through, you could travel at speed. The next thing this does, and you can see in this diagram in the bottom right, is that from where this triangle of cities was connected, now it makes this smooth connection. And the total infrastructure length is greatly reduced because we can have this overlap between our paths. Step 2, select a specific region to analyze. Here what I've done is I've selected the region between Toronto and Quebec City, and I've input several maps and data sets representing different values. These values can be those of social equity, sustainability, and socioeconomic performance. For example, reward routes that travel along existing infrastructure and avoid conservation land. Step 3, test thousands of routes. What I've done here is sampled thousands of variations of a single route between Toronto and Quebec City. The highest performing routes breed with others to continually evolve. So you might ask, how would you quantify the performance of different routes? This is multi-objective evolutionary Hyperloop route optimization, or the Morrow methodology, which uses multiple goal objectives to present planners with a simplified, holistic perspective of key routes to analyze further. You can see on the left here, this is the projected social impact, or the product of X number of social maps, each with their specific biases. These social maps can be anything from a Hyperloop route traveling through a small town, traveling over different protected land. And this environmental impact would be a product of the environmental maps. So what is the effect of different routes on the environment? Is it traveling through conserved land? Is it traveling over farmland? Is it traveling over many rivers? Does it have to span over large areas that might have an effect? And what we can do is we can continually evolve this system and have these open conversations to figure out what is the best way of approaching these objectives, and how can we then find these areas of opportunity to develop our Hyperloop routes further. This third objective is the technical performance. This comes from a calculation of curvature, as well as the product of the impact of massing maps and topographical maps. So the technical performance, you wouldn't want your Hyperloop route to curve lots, but you wouldn't mind it curving above a certain threshold. This also takes into consideration what kind of massing and boundaries and barriers, what kind of hills or valleys is the route spanning over or tunneling through. And of course, this to be able to have this run quickly, you don't want it to take too much time. You want this to be as quick as possible so we can find these moments of opportunity from as many considerations as we want. So what we can then do is actually have hundreds or thousands of maps and actually have each of these paths here, each of these routes, be able to sample from those different maps and find the best options. Step 4 is micro-scale technical optimization, which is in development. The idea here is to select the highest performing routes from the last optimization and shift sections of the route vertically and horizontally across the landscape to reduce curvature, reduce the total calculated column height and tunneling distance, to reduce the material use and construction cost. So what we can do here is make very microscopic changes. While microscopic to a large system are actually very big changes. We can have routes slip across mountains. We can have them test different variations of tunneling versus bridging. As you can kind of see here in this little sketch, we have this route that spans and tries to remain this very fluid path over this very curvy landscape. And there's this one option where it actually travels over this hill here, and it has to span bridges across. There's another option, however, where this blue route, it actually digs through the hill. And so this allows for the use of a lot less concrete, but it might be more expensive to tunnel. So there are a lot of things we have to consider and continually develop the system. So to sum it up, the step 1 is macro curvature optimization at the continental scale. Step 2 is to select your region and input maps, assign biases, and set objectives. Step 3 is to evolve routes according to those objectives. And step 4 is to make micro technical optimization according to those selected routes. What is important here is that there is significant opportunity for direct stakeholder engagement at each step. We can be transparent with how we're planning this infrastructure, and we can talk to people and be transparent about what are the biases, what are the maps, what are the rules we're putting in place to determine the output. So, how will the new high-speed infrastructure connect with existing infrastructure? This is when it gets a little bit fun. The idea here is that a traveler can depart from their local train station and arrive in any city connected by a hyperway, which is a Hyperloop infrastructure, without the need of a large station. So this is pretty exciting, and this is how we're going to do it. You start in the top left here. You start at home, and you either take public transit or an electric autonomous taxi to get to your local train station. And there's a variety of different ways you can do this, but this is just the one story arc that we're following. Once you're at your local train station, you start traveling in the direction that you want to be heading. And I guess I'll go back for a second as well. From when you're at home, the idea is that you would order this trip as though you were ordering an Uber ride, except this ride is across multiple modes of transportation, and it actually tells you which train to get on, when you have to be in different areas if you're taking public transit, or if you're getting picked up by this electric autonomous taxi. Your luggage, for people with accessibility issues who might not be able to carry it, your luggage can actually be automatically taxied from your home to the train station, and then your luggage will be taken care of for your whole trip with autonomous conveyor systems and small luggage robots wheeling your luggage from cargo areas and then elsewhere as well. So there's all these benefits we can produce here. So once you're on your local train heading in the direction it tells you, and you're on the right train, what we can do is actually propose backwards compatible decoupling attachments. So this means that no longer will you have to wait for an express train or a local train. These trains will actually be able to be shared. You'll just have to get in the front half, the back half, or somewhere in the middle. The app will tell you exactly which car to get on. This means that local trains will be able to depart at higher frequencies with lower volumes without increasing emissions. The train that decouples behind will stop at a local micro stop. So these micro stops, we don't need buses or vehicles to be able to access them. We don't need giant parking lots. We can use existing unused land, for example, land beside highways, brownfield sites, And we can have these very small, you can kind of see up in this corner here, it's just a little jut out from existing railways. And so what's happening here is that as this GO train jets out, it's met on either side with two open-air hypertrains. So this means that we can have our Hyperloop trains, our hyper trains, actually be able to be out in the air with outside of these vacuum tubes. And after you leave your local train, you hear the GO train, you'll be told on your phone to be able to enter specific cars of one of the hypertrains on either side of you. What this means is that just from getting on a local GO train, you can actually go in 8 different directions. You can go to 8 different cities by getting to the GO station at one time without having to go to a giant train station. Essentially, all airports and train stations, there are these moments of connection, these moments of intermodal connection. You drive there, you park your car, you get out of your car, you walk over, you walk like 10, 15 minutes even. You go through security, you go through all this, right? And so the big idea here is that instead of lining up and the passenger, the traveler, has to go to the space where all of these different destinations are marked. The idea is that the destinations actually come to you, the opportunities for different moments of travel. So now we have this decentralized system that relies on this decoupling effect. So this is pretty exciting. More work is definitely going to have to be developed here. And we're going to have to test things and talk to more. We have some pretty exciting professionals on our team right now working for Metrolinx, working for TTC. And so we're continuing to talk to them about the feasibility of this, backwards compatibility, all that stuff. So next, this is what I was talking a bit about as well. This is the online check-in system for Intermodal HyperTransit. So again, the idea is that you would start at home. Well, this is the typical trip from Toronto to Montreal. You'd start at home. You might go to the GO bus. You would take the bus to the GO station. You would take the GO all the way up to Union Station, get on the Up Express. You would then be at Pearson Airport. You'd take a flight to the Montreal Airport. You would then go to the metro station, take the metro, and then walk the last mile to your destination. So what this diagram is showing up here in purple, this is the time where your luggage is actually checked, when you don't need to be carrying it around from train to train, from car to train, through an airport, for example. And then these areas down here are your wait and travel time. So you're traveling from home to the bus stop, you're traveling from the bus stop to the station, and then here these light blue areas are moments of waiting. And so one of the biggest, we all know that going on, even taking a flight can cause a lot of anxiety, missing a flight, not showing up on time. And what we do is actually show up 2 or 3 hours early before we get on a flight, not including the travel time to get to the airport. And so this leads to this huge time sink in your travel. And so really what we can do is using this system and as well as what are anxieties of bringing luggage, of being incapable of carrying your luggage, different areas, of walking upstairs, or of trying to find the elevator, all these things, right? So the idea is that from home, you'd be picked up by an electric autonomous vehicle, a mini shuttle that would pick up others in your neighborhood that are also traveling that destination. You would have a little RFID key on your luggage bag. You would scan it and put it in the back. Then you would be taken to your local GO station, local train station. You would take this GO train. You would then get on your micro platform like we showed before. You would get to your hyper station, which we don't even really need. Then you can get to your maglev station. So the idea is that you have this, just like in our body, how we have these We have our arteries and our veins. We have these degrees of circulation. You can think of the aorta in your heart being the moment of greatest circulation. We can almost think of the Hyperloop, the hyperway being the aorta connecting different cities. And as it divides and separates into smaller and smaller destinations, you can think of that as your veins and arteries getting to the tips of your fingers. So we don't need these areas to be the highest speed, and actually we're expecting that. And for example, these areas will be using existing road and vehicle infrastructure. And so the idea for this whole trip is that as you go from one mode of transportation to the next, is that your luggage would be taken with you, and you wouldn't have to worry about it. And so this actually reduces the time it takes for a passenger to get from one mode of transportation to the next. It will reduce your travel time. It will be able to increase the speeds, which we could start sending off our different transportation or modes of transportation. And then down here, this was just this idea of a backwards compatible hypertrain that could travel along existing railways as well as our proposed hyperway. So and we can go into that later if you have any questions. So how does HyperTransit reduce cost of living apart from transportation? So we have the transportation side figured out. That's great. And the big question is, how will this infrastructure be funded? How is this actually going to be made? And so our plan is to develop, like I was mentioning before, transit-oriented communities that have integrated vertical farming. And because of the scale of the developments, because of the materials used, because of the innovative building science and manufacturing techniques, because of prefab design, because of how we're getting our materials and where we're getting them from, we can actually make these affordable developments, but still luxurious to live in. We want to have year-round interior public green spaces. And this depicted here is one idea of one conceptual rendering of what one of those transit-oriented communities might have. Here is just some more visualizations of the connection actually to the platform, and then also what are these interior public community spaces looking like, and how can we develop construction architectural systems to be able to efficiently meet the demand of housing, of the different commercial, retail, workspace, office space of contemporary Canadian life. So I'm going to stop it there. I think we're made pretty good time. And now I'll just open up to some questions, or if there's any areas you'd like me to talk about more, then I'd be more than happy to do that.
Thank you, Rick. I just have a couple of questions for you. What got you into this world of sustainable transportation, Hyperloop, and all that, and why do you keep on pursuing this and do you think you can pursue this as a future career?
Yeah, totally. That's a great question. So the team captain of the University of Toronto Hyperloop team, he asked me to make some renderings of their pod, because at the time I was an architecture student and I wasn't familiar with the engineering world or with engineering teams of the University of Toronto. And so I got super excited about the project. I said that makes a lot of sense. A train that travels at the speed of an airplane. It's a vehicle that has the resistance, the aerodynamic resistance of a plane up in the lower pressure atmosphere on the ground. And so I said, what, that makes a lot of sense to me, and I'm really excited about it. And so I started making these renderings of conceptual stations, because you needed the pod to be and have this background. And eventually, I started asking more and more questions, because I was always curious. What would the implications of actually doing this look like? What would you need to make it actually real? And I figured some of the biggest things were, all right, this is a very huge infrastructure project. The infrastructure behind this is where it's all at. The cost of the vehicles, of the hypertrains, the cost of the stations will be really nothing in compared to the hundreds of kilometers of infrastructure. So I started getting interested in that. And from there, I couldn't answer any more questions. And so I started asking some of my architecture friends to come on and join me on this project. I first asked John Shen, who's the project manager of the team now, to come on. And what we did was we started recruiting more of our A team, the architecture students that we've worked with in the past that we found were doing the best work. We got up to 15 members designing Hyperloop stations and infrastructure from like in 6 months. And by the time we've been working on it for a year, of course, we've been working on it for a year and a half now. But at that 1 year mark, we had recruited about 85 students and professionals from around the world. And now we're working with professionals, like I was mentioning before, from Metrolinx, from TTC, from Airbus, from all over, and we're working to make this a reality. And so, I really have a background in parametric design and computation, and so that means that in my 4 years of architecture undergrad, I never really learned how to make all the technical drawings of a building, figured out how buildings work. But what I did learn was, the ability of critical thinking and the abilities of using computation to perform complex tasks, and of course, to be able to render and visualize them. And so this actually was the perfect project for me, and I've just continued to pursue it, and it's been really exciting so far.
Yeah, that sounds pretty cool and amazing. Also, there's been a lot of, in your presentation today, a lot of very technical and very complex topics and terminology. For people that don't really have that type of background, is there a way that you can like kind of simplify it for them to understand it easier?
Yeah, totally. Specifically with the route optimization. Let me just go back. Oops, too far. Yeah, so one way of simplifying this, actually, there was this one project where Tokyo's subway systems, its subway stations, were mimicked with these pieces of food. And they laid out these pieces of food on the ground or on a table or something, and what they did was they introduced this slime mold. And so the slime mold started to grow along this surface and connect to these different pieces of nutrients. And so what it did was it actually, any areas that it grew that didn't connect to those nutrients, it stopped growing, and it continued to connect between the moments of nutrients. And so one area that this could be seen as is, this is kind of like a growing organism that grows across North America and seeks to, exist and connect between these moments of nutrients. Here, maybe actually that made things more complicated. I don't know. Here, what I did was I just took, essentially these are pixel images of these maps, and this line was drawn along those maps. And wherever this line hits these black areas, that's where it starts to read, oh, there's something here. Or in a gray, wherever this line intersects with like a gray pixel, it'll say, okay, there's kind of something here. And so what we can do is be able to say, okay, for a map such as Canadian populated places, we want to be able to connect to the highest population areas, but we don't want to be able to connect to smaller towns. You don't want the hyperway running through small towns. So we can say for areas where there's a lot of intersection, that's actually good, but for areas where there's little moments of intersection, it's actually bad. And so all that is the frequency of those dark moments where a line will hit along like a black pixel or a white pixel, for example, and all of that just leads to these thousands of different routes, and you can have a very simplified objective. Actually, you could say, okay, this is my one map. This is a slope map. So this is the change in slope over time. So a flat area will be black, and I think a flat area will be like gray, and an area that slopes up will be very, very light, and an area that slopes down will be very black, I believe. I'm not even sure. But what you can say here is, I want these routes, these lines, to reduce the amount of grade change. And so what they'll do is they'll say, okay, the more white the average pixel is for a line passing along this map, I want you to be able to, I want the program to kind of forget those ones. I want it to be as dark as possible. And so what you can do is you can add up all the pixel values from the start to the end, and the lower that final number is, the better it is. And so what it can do is test one route, test another. One number might be like 500. It's just an arbitrary number. Another number might be 700. Another number might be like 200. And so the 500 and the 200, these are just these lines that the sum of the pixel values. Those will then come together and say, okay, we should make some children. And so then those two curves will, those two lines will make, more children that are more in the black areas. I don't know if that helped at all. And then lastly, like this here, that slope, for example, was one objective, was one map. And so you can have a bunch of those maps with a bunch of those numbers that lead to these objectives. And an objective is just a number, like before. So the higher the sum of the pixel color value along a line, the higher this is going to be. And so we actually want these to be lower. And so we want to reduce the social impact, reduce the environmental impact, and then have this technical performance be as low or be as optimized as possible. So what's interesting here is that a lot of these things are counterintuitive. So the more a route will travel along, will travel away from like cities, the more it'll travel on like natural land, right? And so how do you find the balance between natural space and urban space? So this is what it's trying to do. It's trying to balance those two. And then here for technical performance, it's there's all sorts of stuff that go into it, but this is just kind of saying, okay, I don't want my line to be really curvy, to be turning constantly. I don't want it to be hitting on houses, on towns. I don't want it to be going over hills and through hills and over valleys. So this is just a way to say, how can we start to quantify the quality of different Hyperloop route options? And then how can we compare them? And the faster you can quantify them and the faster you can compare them, and then you can start outputting ones that are high performing according to your objectives. So, and then this last step here was just saying, okay, from those outputs, which can be, let's say it travels over, 100 kilometers of farmland, it travels through over a couple of hills, it has to bridge over certain valleys. How can we reduce the sum height of these columns so that we don't have to use as much concrete or mass timber or steel potentially? And some of those little tweaks can actually make a big difference. So this is just kind of like if you were building a highway and if it was traveling through like I know in Oakville there's in front of the police station in Oakville there's this giant super old, I think it's an oak tree, and so what the road did was the road actually just split around the tree and went forward again. So we can start to automate these processes of avoiding objects and being, using less concrete and all that stuff. So this is just a way of tweaking the outputs. And really, other than that, these are just kind of ideas for approaching a more optimized system. And and it's kind of just also continually having these conversations, continually being exposed to these ideas where we can continue to talk about them and brainstorm together, because that's what's most exciting for me.
I see. That's great to know, and it's also very informative. So if there's any more questions from anyone in the audience, you can ask them now. If not, I'd like to think. Yes, there's a question. You can either type in a chat or unmute yourself and ask.
Hi, Rick.
Hello.
Hi, how are you?
I'm good. How are you?
It's a great presentation and it's fantastic. Thank you for all the information that you provide for us. It's very eye-opening. And I have a couple of questions. And I think I love the idea of the HyperTransit infrastructure integrated with the vertical farming. And for you guys, when you do the planning, or and is there any difficulty or problem that's the major thing that you guys always come across? Is it because of the soil or the land, and is any other? I just want to see any other difficulties that you guys facing, because for Hyperloop thing it's a huge project, right? That's one thing I like to know. The second thing is, like, for example, if we build a Hyperloop from Toronto to Montreal, what is the timeline that you guys are looking at?
Well, can you just ask that first question again? What difficulties were we having?
When you do the planning, so what's the difficulty major? Like, is it because because say, okay, for example, if you build a Hyperloop from Toronto to Montreal, like they're between these two cities, right? So what like area that you guys will first look at, like geographical area, or like which, as you mentioned, that which routes you will try different routes, right? Do different proposal for different routes. So just want to see, like, usually what's the difficulties that you guys are facing when you do the planning.
Totally. So this brings up just one point that one of our members, Lin Yi, brought up last year when we were talking, was that high-speed rail in China is very efficient, and North America has to catch up to other countries, just like especially China. They have some of the, I think, the longest high-speed rail infrastructure in the world, and one of the difficulties he was saying of that infrastructure is the accessibility. So if it takes you usually 3 hours to travel from city A to city B, and it takes you 30 minutes during taking a high-speed rail, but if you have to drive 40 minutes to the train station and then drive 40 minutes from the destination train station, then you almost might as well just drive or take a different mode of transportation. So one of the biggest problems we had was addressing the density found within cities. How do you integrate such a spatially large infrastructure into cities with so many barriers, so many obstacles? And so one of the big things is tunneling is going to be really important. We need to tunnel under high density urban centers to connect to the downtown cores. And specifically along the way, we have to connect to transportation, public transit. That's the biggest thing. We have to connect to existing public transit infrastructure. And so one of the biggest difficulties we had was okay, if we want to current tunneling for subways for LRT can get up to $60 million per mile from different Metrolinx projects. So these are very expensive and will be like triply expensive with Hyperloop. So we need to make sure that with some of the biggest problems was just connecting to downtown cores. So a lot of that is just going to be engineering and figuring out the least expensive, most safe way to tunnel and to build that infrastructure. In terms of other difficulties, I think some of the biggest ones are with any infrastructure, there is going to be inequities. So which communities are being given the value, the amenity of that accessibility to high-speed rail. If we have like a little underground subway stop for Hyperloop in a community that has the potential of being gentrified, so this means a community that predominantly rents, community that has a predominantly low household income level, community that is predominantly visually minorities. We don't. There's all sorts of difficulties that go through, especially social issues that go through developing and proposing this infrastructure. So we've definitely had a lot of difficulties, or not difficulties. There's challenges that we have the opportunity to address and solve. But I think we just, the stakeholder engagement is going to be one of the biggest things, because if this infrastructure isn't accepted, if it's not seen as it's safe, if it's seen as too invasive, obtrusive, then it's not going to be able to get the public funding, or private funding isn't going to be excited to fund it. So these are some of the biggest things that we found. High density obstacles are high density urban centers, connecting to those, as well as stakeholder engagement, social equity. There's a lot of complex things that go into infrastructure, specifically. And then, like, historically, rail infrastructure has been used to segregate different neighborhoods and different communities. Has ties to Jim Crow laws, ties to redlining, all that stuff. But so one of the things we want to make sure is that this infrastructure is elevated off the ground in urban centers, if it's not underground, so that it's not actually creating this divide between communities, and when it gets out into nature, that it's not blocking migration paths, it's not dividing environments like roads really do, especially highways with different barriers and all that. So those are some of the biggest challenges we've had, and then specifically retrofitting, backwards compatibility, a lot of engineering, signaling systems. How would you ever go about implementing this high-speed decoupling? That's a long conversation, a lot of engineering to go into that, as well as, and then I'll just move on to your next question, like what is the timeline here? So one of the exciting things is that we can have these this multi-stage integration process, where it's not just, okay, one day there's just your current infrastructure, and the next day you have this 20-30 billion dollar infrastructure project that just appears. What we want to be able to do is slowly integrate optimization to existing public transit within the next 5 years. Whether that's through, and currently there's optimization being done already with regenerative braking systems, and autonomous. I'm sure those of you in Toronto have seen the autonomous, the signs for autonomous subway and maybe streetcar systems, and So that's pretty exciting that, already our infrastructure is getting better, but there's a lot more we can do in the short term without building this infrastructure like outright to make this a reality. Then, also what we can start doing is one of the big ideas we had was that we can get funding and build solar panel farms and wind farms on brownfield sites that in the future will be the locations we've found have been optimal for these large mega hubs, and that will pass along our our infrastructure. So we really want to be able to transform farmland back into forest land, and do all sorts of other things. Reintegrate indigenous fauna and flora. Really produce carbon sinks in the short term, and then in the future build off that. So really, this is a project. Once we get more stakeholder engagement, once we get more funding, we can start working on this within the next. We can start having working with real land within the next couple of years. So that's kind of like the 2-year timeline, along with building machines that will make this a reality. Bridge builder machines, super exciting. Thinking about, we've got a lot of stuff in the works, but there's a lot of stuff we can do in the short term to make this a reality. And then, depending on if we can have automated maintenance, automated robotic construction, prefab elements. There's a lot of stuff we can do to be able to build this really quickly, if we can gather the materials for it, and all that. So this project really within the next 20 years, could very well be a reality. And until then, what HyperTransit can do is act as a consulting service to determine the feasibility of different routes around the world. So with our Moro analysis, what we can do is input maps from in between any cities and be able to say, okay, this is the area that's the most promising, or these 3 general areas are most promising to have a route. And we can work as consultants, we can work as all sorts of stuff. So there's a lot we can do in the short term, which is really exciting. And as a potential startup, we are looking for talented young innovators and for professionals to join us as volunteers, as we all are, so that we can make this into a future into future careers for ourselves. So it's pretty exciting. Sorry if that was an extremely long-winded answer to your questions, Anita.
That's great. That's great. Yeah, that's very exciting. And then even for a short term, and yeah, I think we're really looking forward, like even doing like a 10, 20 years plan that is all good for the community and the environment, and it is fantastic. Thank you, Rick, and your team, and whoever get involved in this Hyperloop system. That I think is the future for the communities.
Totally. Yeah, I believe that too.
Also like to give a big thank you for Rick for giving his time and research for us today. So thank you, and hope everyone has a great day.